Today, we are from Group 8. We are going to present about the RAM study for a gas processing plant. In this slide, you can see our members include of Shaza, Haziq, Wong Kai Chen, Takif, and Awang.
Okay, so for the project background is first of all we will get to know the gas plant first, which is the purpose. The purpose of the gas plant is to process raw natural gas by removing impurities and recovering valuable byproducts to produce pipeline quality gas. So for the plant inputs, the plant receives two gas streams, a medium pressure and a high pressure stream, each with a volume of 50 million standard cubic feet per day for a total input of 100 million standard cubic feet. So for our approach is a reliability block diagram has been developed to represent the plant. This RBD is based on process flow diagrams and piping instrumentation diagrams, focusing on the reliability-wise relationships between equipment. Now is the breakdown of the main processes inside the plant. So in this plant, it has 8 main processes. The first one is the medium pressure separation and compression unit. Next is high pressure separation unit. Then feed gas compression unit, acid gas removal unit, amine regeneration and sulfur recovery units, dehydration units, natural gas liquids recovery units, and lastly the residue gas compression.
Hi and Assalamualaikum. I am Resha Zadana. Now I will be explaining the problem statement of this project. This study focuses on the frequent equipment failures and inconsistent repair durations observed in a natural gas processing plant, which have significantly impacted operational performance. These issues point to potential weaknesses in the current maintenance strategy, especially in critical units like separators, compressors, and turbines, whose reliability and maintainability directly influence system availability and cost. To address this, we conducted a comprehensive RAM analysis using tools such as Weibull++ and BlockSim.
Thank you, Shaza. I'm Kaishans. For this slide, I'm going to explain about the objective of our project. First, we are going to establish the assumption used for our study. And second, we are going to evaluate the average availability of the plant for a period of 5 years based on the failure and the repair data gathered from the plant. And thirdly, we are going to identify the critical equipment that contributes to the availability figures that we gathered. And finally, we are going to propose our justified action plans that are crucial for us to increase the availability of the plants until 99%.
Before conducting the analysis, several key assumptions were established to ensure consistency and validity of the results. First, we assume independence of failures, meaning each failure event is not influenced by previous ones unless a trend is statistically detected. We also assume that all failure time data is complete, accurate, and not subject to censoring of truncation. In terms of the analysis methods, we assume that the statistical tools used, graphical trend tests, man tests, and Laplace tests, are appropriate for detecting trends in failure data, and all interpretations follow standard hypothesis testing at a 5% significance level. For the reliability block diagram modeling, we assume that failure and repair data are generalized across similar equipment types for consistency in simulation. Lastly, for throughput, we assume gas flow is allocated using a weighted approach across all operational paths. These assumptions form the basis for the reliability and maintainability analysis carried out in this study. For all equipment, we perform three trend tests to evaluate the failure behavior over time: the graphical trend test, the man test, and the Laplace test. For example, starting with the graphical trend test, we plotted cumulative time between failures against failure number. A second order polynomial fit representing the NHPP model gave an R-squared value of 0.9691, higher than the linear HPP fit at 0.9129. This suggests a nonlinear trend indicating increasing failure frequency or system degradation. Next, the man test showed 9 total repairs and 4 reversals. At a 95% confidence level, the acceptance region is between 9 and 27. Since the observed value of 4 falls outside this range, we rejected the HPP assumption, further supporting the presence of a trend. However, the Laplace test gave an L value of 0.392, which is below the critical value of 1.96. This suggests no significant trend and supports the HPP model. Despite this, due to the strong indications from the other two tests and the critical role of the separator, We adopted the NHPP model as a more conservative and accurate representation of its failure behavior. This approach was consistently applied to the rest of the equipment for thorough RAM analysis. Now, for data analysis, we analyze failure data using recurrent data analysis in Weibull++, applying a correction factor based on trend results, Q equals to 1 for NHPP and Q equals to 0 for HPP. The power law model helped identify increasing or decreasing failure trends using beta and eta parameters. Maximum likelihood estimation was used to fit both failure and repair data. MTTR values were then input into BlockSim to simulate real-world availability. Exponential repair times indicated consistency, while log normal and Weibull showed variability due to factors like complexity or human error, supporting better downtime modeling and maintainability planning. Tables in the slide showed an example parameters of three of the equipment after analyzed in Weibull++.
Thank you, Shaza. Now I'm going to explain about the block sim. Under block sim, the block is modeled according to the data given under the case study, together with the throughput data with start and end volume of gas at 100 million standard cubic feet per day. Total, there are 7 subsystems for the natural gas plant, which consists of MP separation and compressions, high pressure separations, feed gas compressions, acid gas removal, dehydrations, NGL removal, and amine regen and sulfur recovery unit. The final figure here shows the overall natural gas plants model under the block C. The result shows an average availability of the natural gas plants at 88.61%. Across a period of 5 years, the natural gas plants recorded an overall uptime of around 1,617 days and an overall downtime of around 208 days. The mean time between failures is recorded at around 7 days, indicating that around 1 week of running the plant, we might be experiencing failures, and it takes around 1 day to maintain the plant to be running again as indicated in mean time to repair. All failures are assumed to be corrective maintenance with no predictive maintenance recorded. Additionally, the number of corrective maintenance recorded in 5 years is around 222, indicating that further optimizations is needed to increase the availability of the plant and reduce its downtime.
So looking at the block downtime criticality ranking, the assets that are considered as high criticality is the demetallinizer, filters, reflux drum, and compressors. This has a risk score from 12.30% up to 23.4. This contributes most of the downtime and require immediate maintenance bonus. While for pumps, discharge drums, and separators, these are considered as moderate criticality. They only require consistent monitoring and scheduled maintenance. For the low critically assets such as suction drums, exchanges, and slug catcher, with risk score below 3.5%, the maintenance can be scheduled with more flexibility in order to reduce costs.
To achieve our target of 99% availability, we carry out several improvement iterations based on the Downtime Critically Index or DTCI. Initially, the plant had a low availability of 88% with the demetanizer and filters contributing the highest DTCI values and over 20%. So our first improvement was to add standby units to these two critical components, which immediately increased the availability to 90%. Next, we focus on the reflux drum and drive turbine, which still show high DTCI values by improving MTTR and adding another standby unit for the reflux drum and drive turbine. We raised the availability to 92.2%. Further improvements were made to components like the suction drum, sweet gas KOD, and discharge drum by introducing redundancy, which brought us to 98.8%. Finally, minor adjustments like adding standby filters and optimizing coil separator configuration and push us to 99% availability. Each step was guided by block sim simulation, targeted high DTCI contributors while balancing redundancy and maintainability. This is a diagram of the block sim that we made for the improvement to achieve 99% availability of natural gas processing plant. To conclude, this project evaluated the plant's availability over 5 years, achieving a 99% availability rate after implementing 4 key improvements. We identified critical equipment like the demetanizer and drive turbine as major contributor to downtime, By focusing on this, we minimize system failures and boosted operational performance. For recommendations, prioritizing equipment based on its criticality is key. High critical equipment require a predictive maintenance and enhanced monitoring, while medium critical assets should undergo regular inspection. Implementing a reliability-centered maintenance (RCM) and upgrading low MTBF machinery can further improve system reliability and reduce recurring failures.